Hello everyone, welcome to problem 2.7. This is going to be a rather long video. I want to kind of go through problem 2.7 a little bit in detail. We're going to do all the math. We're not going to skip any integrals. We're going to do all the integrals by hand. But yeah, it's an interesting problem and one of the harder ones starting off in the textbook. So the problem says that we want to find the electric field at distance z from the center of a spherical surface of radius r that carries a uniform charge density of sigma. And it says to treat the case where z is less than r, which means inside of the sphere, and where z is greater than r, which is outside of the sphere. And we're going to solve just kind of the general case, and we can kind of evaluate at the end, once we have our answer, what the electric field will look like when z is less than r and z is greater than r when we're done. And it gives us some hints to use the law of cosines to write our script r vector, and it says to let's see, it just gives us some hints like just taking the positive square root of things and things like that. So anyways, I just want to kind of explain this diagram real quick. So we have our spherical surface. Just sort of imagine it's a three-dimensional sphere. And I've defined some angles. So this angle here, phi, is on the polar or the xy plane. It's the angle from the x-axis. And this is our origin, and so this is the radius r. This goes all the way out to the surface of the sphere, where I've sort of carved out a little differential area of charge on the sphere, dA here. So you can think of this as being like a dA, and which carries a little bit of charge, dq, on it. This is our field point, so we're just a distance z from the sphere, from the center of the sphere. And this distance here is the distance from our charge, our differential amount of charge on the sphere, dq, to our the point we're trying to find the field at. Then I defined this angle as theta, the angle from the vertical axis, the z-axis, and this is theta, and this angle I've defined as gamma. And we'll see how all these come into play here soon. So real quick, since this is a very symmetrical situation, if you were to think about, hey, what is the magnitude of this field that this little area of charge produces here? Well, you can think of it as being a little point charge, and it would produce a field up in this direction, this way, and you could find an equal and opposite charge on sort of the other side of the sphere and find, which is kind of on the back side of it. But what you will find, I think it's perfectly reasonable for you to kind of see how the x and y components of the electric fields for this would all cancel out, and all you're going to get is the radial, vertical, like all just the z components, all the components just pointing directly away from the sphere. And so my argument here is that only the z components of the electric field from every piece of charge on the sphere matters. And so we just need to add up all the z components of every piece of charge on the sphere. All right, so let's get started. I'm going to move the diagram away. I'll bring it back a couple times just to kind of allow us to look at it a bit. So we have that the z component, the differential amount of, the differential amount of field that it produces would just be 1 over 4 pi epsilon naught, and then dq, which is the charge on that differential area, over the distance between that piece of charge and our field squared. And since we're trying to find the z component, we need to multiply by the cosine of one of our angles. And let me show you which angle it would be. So if I were to draw out this field, right? So this piece of charge produces an electric field in this direction, as we said. Kind of draw it out here. And if I were to draw out some of the components here, you can see that this angle gamma would be the same as this angle here. This is also gamma. And so the vertical component of this field, and there's also a x component, I guess, but it's coming out of the page, I guess. But anyways, we're just going to worry about this because we're just trying to find the vertical component. So we're going to use the cosine of gamma to pick out the z component of the field. So we multiply this by the cosine of gamma. Okay. Now, how can we express dq? So dq is our charge per unit area times dA, which is the area of that tiny little piece. And in spherical coordinates, we're going to be working in spherical coordinates for this, which just makes sense. A differential area is expressed as follows. So we have sigma, then we have r squared, sine of theta, then we have d theta, d phi, where r is the the radius. And then how can we express the cosine of gamma? So here we got everything in terms of theta and r and phi and stuff, but cosine of gamma is not expressed in terms of that. So how can we do that? So cosine of gamma, we look at our diagram again. You can draw a straight line here across from here and sort of make two right triangles out of these two pieces. And I tried to draw that as clear as I could. And so we can use this triangle here to sort of find the cosine of gamma. Since this is a 90-degree angle, we have a right triangle. So cosine of gamma is going to be this distance here, which I called z prime. Since the total distance from the origin here is z, I called this distance here, this segment, z prime. So it'd be z prime over script r. But how can we express z prime? Well, z prime is just our total distance minus this first part. So it'd be z minus something. Well, this is also a right triangle, and this segment of the triangle, this side can be expressed as arc times cosine of theta. So this distance here is just z, the total distance, minus r cosine theta, so taking off of this segment of this triangle. So z prime is z minus r cosine of theta. So we have z minus r cosine of theta. I'm trying to make this geometrically as clear as possible. Over script r. And again, where script r, well, now we're going to use this entire triangle here, and it's not a right triangle, and we're going to do it in terms of theta, so we can use the law of cosines, which it gives us, is one of the hints. The law of cosines we can use to find this length here. So using the law of cosines, script r is, and I'm just assuming you know what that is. If not, I would suggest looking it up and just learning a bit more about the law of cosines and how it's derived. But we can write script r as a square root of r squared plus z squared minus 2 rz cosine of theta. All right, so we have all of our ingredients, so we can plug everything into here and find that dEz is equal to 1 over 4 pi epsilon naught dq, so we have sigma r squared sine of theta times the cosine of theta. So then we have z minus r cos of theta on top And then we have script r squared, and then we have script r, so we're going to have script r cubed on the bottom, which is going to be r squared plus z squared minus 2r z cosine of theta to the 3/2 power. And then don't forget our d theta and our d phi. Okay, so that should be everything. Yeah, so this is the differential amount of field in the vertical direction, the z direction, that a single piece of differential area on our sphere produces at that point in space. So now all we have to do is integrate this over the entire surface area of the sphere to get the total electric field contribution of all the little pieces on the sphere. So let's go ahead and write out that integral. So I'm going to try to pull out all of our constants. So we have sigma r squared, that's constant. Z minus r cosine theta, that's going to be part of the integral. So we have sigma r squared over 4 pi epsilon naught outside. And then this only depends on theta, this only depends on theta. So we're going to have our integration, a double integral. So to integrate over the surface area of the sphere, we're going to integrate from phi, which is that polar angle on the xy plane, from 0 to 2 pi, meaning we're integrating all the way around the circle, all the way around the plane. And just d phi here, I'll just throw that in. And then we have our integral with respect to theta, which is the angle from the vertical, the z-axis, which runs from 0 to pi, and these two integrals will get us all the way around the sphere. And then just everything that depends on theta. So we're going to have, I'm going to write the bottom first. We have r squared plus z squared, 2rz cos of theta to the 3/2 power. Then we have sine of theta times z minus r cosine of theta, and then times d theta. All right, so this is a rather tough integral to solve. And real quick, we can just get rid of this first integral. So the integral with respect to d phi is just phi. And then from 0 to 2 pi, well, that'll just be 2 pi. So we can already pull that out. And I'm not going to cancel things quite yet. So I'm going to write 2 pi sigma r squared over 4 pi epsilon naught, and then we just have our integral. Oh, I should write that. So Ez is equal to this, right? The total electric field in the z direction. I should have just wrote that in the first place. So we still have this integral now to solve. I'm going to write everything out. I'm going to try to go as slow and methodically as possible because this is going to be a tough integral to solve and I don't want to make any mistakes. But if I do, I will try to correct them. Theta. All right. So how can we solve this integral? This is a rather tough integral to solve with respect to theta. It's not really in a form that we can really do anything with our standard integral tricks. But we see that we have sine of theta d theta on the top, and we have cosine of theta in our thing. So this kind of calls for maybe like a u substitution, because you know the integral or the derivative of cosine of theta is sine of theta. So let's try to do a u substitution of. So let u equal to cosine of theta. Then du with respect to theta is a minus sine of theta d theta. Okay, so plugging that into here, we're going to have 2 pi sigma r squared over 4 pi epsilon naught, and this minus sign, so sine of theta d theta can be replaced by minus du, so we're going to pull the minus sign out front. And then our bound is going to run now. So u, when theta is 0, then cosine, then u is 1. And when theta is pi, cosine is -1. So our bound runs from 1 to -1 now. Sorry about that. And so now we have on the top, let's see the bottom first. So we have r squared plus z squared minus 2, minus 2r z u, and still to the 3/2 power. And on the top we have z minus r u du, because sine of theta d theta is our du now. All right, so now we move on to solving this integral here. So we had got our integral into this form, and I had initially, I'm re-recording this because I had initially messed up my bounds. What I'm going to do is take this minus sign that we have and use it to flip the bounds of this integral, and we're going to solve this integral ignoring the constants, and when we get our solution for this integral, we'll go back and you know, make sure we get the constants back. But I'm going to rewrite this integral with the bounds flipped, and let's just write it out here. So we have that our electric field, actually no, since we're just solving the integral, it's not exactly the electric field because we're ignoring the constants, but our integral applying the minus sign is going to be from u equals a -1 to 1, and we have r squared plus z squared minus 2r zu, and we have z minus ru on top, du. Okay. From here, we're going to make a u substitution again. However, we're using a different variable. So our substitution is going to be v, and we're going to let that equal to what's inside of this. Oops, forgot the 3/2 power. What's inside of this 3/2 power here? So it's going to be equal to r squared plus z squared minus 2rzu. And that way we can solve now. So if we take the derivative of this with respect to u, so dv is equal to minus 2rz du, so that we can get du in terms of dv. So it's minus 1 over 2rz dv. So this is one substitution we're making for our integral. I'm going to just go ahead and circle this. And then we're going to replace what's on top here, z minus ru, in terms of v, since the bottom is already in terms of v. So how can we do that? Well, in our substitution we have minus ru here. So let's go ahead and try to solve for minus ru. So just doing the algebra, minus ru is equal to v minus r squared minus z squared divided by 2z. And then if we want z minus ru, we need to add z to both sides. So I'm going to do that algebra over here. So we have z minus ru is equal to, we have v minus r squared minus z squared over 2z plus z. I was about to write v plus z. And then let's get common denominators. So we have z minus ru is equal to, doing this, we're going to have, so we multiply this by 2z over 2z. So that's going to be 2z squared plus minus z squared. So that's going to be positive z squared. So we're going to have v minus r squared plus z squared on top, and then over 2z. And this is the substitution we're going to use for z minus ru in our integral. All right. So let's go ahead now and let us plug everything in and get our bounds all sorted. So we have, let's see, we're going to have this minus 1 over 2rz out front. So let's have that. Then we have our integral. And our bounds now, v. So if u is -1, then this is going to be r squared plus z squared minus 2rz times -1. So it's going to be a plus 2rz. So that's going to be the same as r plus z whole squared. And then the top will just be a minus sign there. So it's going to be r minus z whole squared for the bounds. Do that, then we have on the bottom 2z times v to the 3/2, plugging in our substitutions, and v minus r squared plus z squared on top, and dv. And then what we're going to do here is take this, oops, sorry, I don't know if you can see that. So this is what I have for the integral after plugging in our substitution for v. And I'm just going to flip the bounds on here, getting rid of this minus sign, so that we have 1 over 2rz times the integral. So we have r minus z squared, and then r plus z squared on top. We have 2z v to the 3/2 power times v minus r squared plus z squared dv. All right, so this is the integral we got to solve, and it's actually in a rather solvable form now. So how can we deal with this? Well, I can actually pull out the 2z, I just realized. So 2z is also constant, so we can pull that out. And we have 1 over 4rz squared, integral from r minus z squared to r plus z squared. So this makes our integral a little bit nicer. Three halves dv. All right, so I think this should be, this actually, you should be able to recognize this is going to be a solvable form. So we essentially are going to be dividing every term here by v over 3/2. So we have, I'm going to bring v to 3/2 to the top real quick, just to make this a little clearer. So we're actually in a pretty solvable form now for our integral. So we have r, my handwriting is getting worse and worse by the day, r plus z squared. So we have our v minus r squared plus z squared to the 3/2 power times v to the minus, sorry, I didn't mean to write that, v to the minus 3/2 power. So this is multiplying by all of that, and we can actually write this now as 1 over 4rz squared. The bounds from r minus z squared to r plus z squared. So this can be written as, we have z squared, we think, yes, so we have z squared minus r squared times v to the minus 3/2, and then plus v to the minus 1/2. So if you can think about it anyway. So if we could divide, since we're dividing all three of these terms here by this, so this is v to the positive 2/2 divided by v to the 3/2, which makes that v to the minus 1/2, or 1 over the square root of v, which is what I have here. And then I've essentially just kept these two terms grouped and multiplying this out, since, I mean, these don't depend on v at all, so they're just constants with respect to this integral. So I can kind of group them like that and do that with respect to dv. And now, if you can see, we essentially have two integrals now. So we have this integral, since integrals split up over a sum, and two very simple integrals. Since we're only integrating with respect to v, this is constant with respect to v, so we just have two power rule integrals to solve now. So this becomes extremely solvable. So let's go ahead. I'm going to move this over, and I can go ahead and write out the answer to this integral. It's pretty simple. So I'm going to write out, so we have our 1/4r z squared, and that's just going to stay on the outside for now. And for the first integral, we still have our z minus r squared, or z squared minus r squared. So that's a constant with respect to the integral, so that's pulled out of the integral. And then the answer to the actual integral, the first integral, I guess, so v to the minus 3/2, if you integrate v to the minus 3/2 with respect to dv, you get minus 2 over the square root of v. Just using the simple power rule for integrals. So you have minus 2 over the square root of v, and then we just add on plus the integral of v to the minus 1/2, so that would be v to the positive 1/2 divided by 1/2, so it'll be 2 times the square root of v. So we have plus 2 times the square root of v is the answer to that integral. Okay, and then we evaluate everything in here from r minus z squared to r plus z squared. All right, so let's go ahead and plug everything in. So I'm just going to keep the 1/4r z squared out for now until we're done evaluating everything. Okay, so what's the easiest way to do this? I'm going to take this minus sign and apply it real quick to this term here. And so this term is just going to flip direction before we evaluate, actually. So r squared minus z squared is what this term becomes. That way this just becomes 2 over the square root of v. And we have plus 2 square root of v, which we can pull. So I guess we have a 2 in each term, so we can actually pull a 2 out of each term. So we know this is evaluated from those bounds. I'm not going to write the bounds over again because we know what they're evaluating between. I'm just going to simplify it even more. So we can pull out the 2 and just make this 1/2rz squared. And then we have our r squared minus z squared. and then we have 1 over the square root of v plus the square root of v. I think that's the simplest form you can get to evaluate. So we're evaluating, remember, from r minus z squared to r plus z squared. Okay, so now let's go ahead and plug in both of these bounds into our v's. So we have r1 over 2r z squared. Let's go ahead and write this out. And r squared minus z squared, I'm actually going to write as r plus z times r minus z. You can, that's just unfactoring, or factoring it out, I guess. And then, so if we plug in r plus z squared into our first term here, and let's do another bracket. So this second bracket is going to be for the first evaluation term. So evaluate this whole thing with this term, and then we're going to do the second term. So 1 over the square root of that, so that's just going to be 1 over r plus z, and then plus the square root of v, so plus r plus z. Okay, so that's our first evaluation, and then we'll have a minus in our second evaluation term. So we plug in r minus z squared. So again, we have r plus z times r minus z, which is just this, just factored out. And I'm doing that because we're going to have a lot of r plus z and r minus z to cancel out here. So then we have 1 over the square root of r minus z squared, which if this was negative, it's squared, so it would be positive, and so throwing in the square root would be positive. So really it's just going to be the magnitude. We want 1 over the magnitude of r minus z, since it would always be positive. And then same thing for this. It's going to be plus the magnitude of r minus z. I'm closing off both sets of brackets here. So this is our term here. So what I'm going to do is kind of get rid of these brackets, the inner brackets, and distribute some terms and group terms and apply the minus sign. Okay, so just we have a bit of algebra to do here to get this in a simple form. So you have 1 over 2r z squared. So let's go ahead and distribute what we can here. So this times this, first term is just going to give us r minus z, and then we have plus r plus z, right? And then we have a minus sign, so r plus z times r minus z times the times 1 over the magnitude of r minus z. So r minus z divided by the magnitude of r minus z doesn't cancel, because r minus z can be negative. This is the magnitude. So what we're going to have is minus 1 over the magnitude of r minus z, and then minus the magnitude, we're going to have r plus, hang on, I did something wrong here. Oh, okay. We're going to have, sorry, I messed up. Since this doesn't cancel, I'm an idiot. Since this doesn't cancel, we're going to regroup this as r squared minus z squared on top. So we're going to have r squared minus z squared on top here, sorry, and then minus the magnitude of r minus z. And that should be fine. Let me just make sure I have this already solved out, but I'm just making sure that I'm sort of doing this correctly. And yes, so we can sort of take the parentheses off now As you can see, we have a minus z, a plus z here, so that z is going to cancel. So we can just simplify this a little bit further. I'm going to flip the page. And we can group some terms. So we still have 1 over 2rz squared. And then we're going to have r plus r, so we have a 2r. And the minus z plus positive z, that's going to cancel. And then we have a minus sign. And I'm going to group these terms with the common denominator, I think. So if you multiply the top and bottom of this by the magnitude of r minus z, with the magnitude of r minus z times the magnitude of r minus z is the magnitude of r minus z squared, which is always positive. So we can get rid of the magnitude sign. So we're going to have on top r squared minus z squared plus r minus z whole squared divided by the magnitude of r minus z. Okay, oops. Sorry about that, guys. So we have 1 over 2rz squared times 2r minus, and remember I distributed or I made a common denominator here. And so that's what we have so far. And we're getting closer to the answer. So let's go ahead and kind of expand that numerator term that we had. 1 over 2rz squared. So we have 2r minus. So here we're going to have just have r squared minus z squared plus r squared plus z squared minus 2rz on top. So let's just write that out. We have r squared, and if it's, so we have r squared minus z squared plus r squared minus plus z squared. So the z squared is going to cancel, and we're going to have 2r squared minus 2rz. So we have 2r squared minus 2rz on top, divided by the magnitude of r minus z. And how can we simplify this even more? Let's see. So 2r is in every term, so we can factor out a 2r. So let's go ahead and do that. So if you factor out 2r, then the 2r here cancels, and all we get is 1 over z squared. So we have 1. We have minus, so 2r. So this would just be r, and then minus 2r, so r minus z divided by the magnitude of r minus z. All right. And I think this is about the simplest we can get for our integral. So this is the answer to our integral. And remember, our original integral was this integral. This is where we started. Well, we started here, and we transformed it down to here. We just have to plug in all of our constants that we had out here. We have minus 2 pi sigma r squared over 4 pi epsilon naught times 1 over z squared. And now we can cancel stuff if we want. So the 2 pi we can cancel. Makes that a 2 on the bottom. So we have 1 over z squared. I'm going to just group this since it's multiplying by all of this. So 1 over z squared times 1 minus r minus z over the magnitude of r minus z. So what we get here is sigma r squared over 2 epsilon naught z squared. I can pull that out. So we have z squared on the bottom. And then times, this is a minus sign here, times 1 minus r minus z, which we could just get rid of. Well, we'll see. So okay. So now this is going to be our integral. So E, or this is going to be our field, our electric field then. I'll just write the total field E, which we know just has a z component. So we have minus sigma r squared, and I need to check. So the only thing I'm not sure about is this minus sign. I'll have to double check on this when we get to the end. If I am off by a minus sign, I will have to see where I went wrong. But I think I have done it correct so far. I think this minus sign came from the substitution for cosine of theta, so I don't see why it shouldn't be there if I didn't include it in my integral. So, all right, so this is our vector, our electric field vector, and what we need to do is evaluate this for the two cases where our point, our field evaluation point, let me bring out the diagram, where z is either greater than the radius r, so outside of the sphere, or where z is less than the radius r, which is inside of the sphere. So we need to find the electric field inside and outside of the sphere. So if z, let's go ahead and write this here. If z is, let's do less than r. If z is less than r, so what we have is r minus z. So z is less than r. So this is positive on top. And r minus z is positive. So you can get rid of the magnitude here. So this becomes r minus z over r minus z, which becomes 1. So we have 1 minus 1, which is 0. And that means this entire field is 0. So if z is less than r, then the electric field actually reduces down to 0. There is no electric field inside the sphere. So if you have a hollow sphere, a hollow surface with some charge on it, if there is no charge within the sphere itself, if all the charge is contained on the surface, then the electric field within that surface and the hollow emptiness is 0. Which is pretty interesting. That's not easy to prove. We have just proved it here. Well, we proved it for a specific case, I guess, but it can be proven, and it has been proven for any generic surface. So now let's evaluate the case where z is greater than r. So outside of the sphere, what happens? So if z is greater than r, then we have r minus z. So this is going to be a negative number, and r minus z, the magnitude of r minus z, that's negative, so that's going to be positive. But we can flip that and just make it z minus r instead. So what we have is this. We have the electric field is equal to minus sigma r squared over epsilon z squared times 1, Then we have minus r minus z over z minus r, which r, so in this case, remember, z is greater than r, so r minus z is negative, z minus r, so this is going to be a negative 1. So we're going to have a minus negative 1, which is going to make this a 1 plus 1, which is 2. So what we have is the electric field is minus sigma r squared. I think this negative sign, I got to check this negative sign, because it should be positive, I think, at this point. But I'll have to double check that at the end. I'll make sure I get this right. If that negative sign shouldn't be there, we'll have to figure out where it came from. So then we have just a factor of 2 on top. So since this is 2. And we can multiply the top and bottom by 4 pi. So this is in the z hat direction, so let me just write that. And then multiplying the top and bottom by 4 pi, well, 4 pi r squared is the surface area of the sphere, times sigma, which is the surface charge density, is going to be the total charge q. Oh, and I forgot, we had a factor of 2 on the bottom anyways. If you look back on the previous page, we have a factor on 2 here. So this 2 here that we pulled out, because this was 1 minus negative 1, actually cancels out. So what we find is that we have sigma r squared, and like I said, we're multiplying by 4 pi over 4 pi epsilon naught z squared. We have a negative sign, but I'm not sure. I don't think that should be there. So 4 pi r squared, remember, is the surface area times the surface charge density, gives us the total charge. So I think that minus sign is wrong in this case, because what we have is 1 over 4 pi epsilon naught times the total charge q over the distance z squared and the z hat direction, which we're supposed to get. I know what the answer should be. So it looks like we are off by a minus sign. However, if you recognize this, this is just the electric field of a point charge. So outside of a uniformly charged sphere, no matter how big the sphere is, it doesn't depend on the radius, the sphere just acts like a point charge. It's almost as if all the charge on the surface of the sphere is contained at the center of the sphere, because it depends on the distance z, which we defined as the distance from the center of the sphere. So all the surface charge on the sphere acts as if it was a point charge at the center of the sphere itself. All right, so that was a rather long derivation and solution for this problem. I'm going to try to figure out the case of this minus sign. But if you enjoyed this video, be sure to drop a like. If you have any clarifications, if you found what I did wrong, or if you've seen any errors in the video, feel free to let me know in the comments. I will try to correct them for future viewers. And yeah, be sure to subscribe to my channel for more content and more solutions on the way. And I'll see you guys next time.